And one second. So, welcome everyone to our third and final day of scientific colloquium. We have our first speaker, Shenwei Huang, and I hope all of us will have an excellent day. We'll learn about research and start.
Okay, so hello everybody, welcome to the event. Today I'm going to talk about coloring graphs without long-induced paths. So my talk has four parts. First, I will introduce you the concept of graph coloring and why people study graph coloring. And then I will give a formal definition of my problem and talk about the recent results in my research area. And in the third part, I will talk about what I have done recently and then discuss some open problems. So what is graph coloring? So let G be a graph with vertex set V and H set E. A K coloring of G is an assignment of colors to vertices of G such that the end vertices of every edge receive different colors. So the following is an example of four coloring of the graph. And you can check for every edge, the end vertices receive different colors. So in reality, we want to color a graph using as fewer colors as possible. This leads us to the notion of chromatic number. So the chromatic number of G, denoted by chi G, is the smallest integer k such that G has a k color. To give you an idea, let's look at example H again. So this picture shows a full coloring of the graph H. So the question is, can we color H use three colors? The answer is no. Suppose we try to color H use three colors, say yellow, blue, and red. So because you look at this H, you have to color these two vertices using different colors, say yellow and blue. Then this vertex and this vertex has to be colored red. And similarly, this vertex has to be colored blue and this has to be colored yellow. But now the center vertex adjacent to three vertices has been colored blue, red, and yellow respectively. So there is no colors for that vertex. And therefore, the chromatic number of H is 4. You can color it use 4 colors, but not 3. And you already seen that it takes a little bit of work to find out the chromatic number of such a small graph. In fact, computing the chromatic number is computationally hard. Before we go to that, let me explain why people study graph coloring and why it is important. So first, graph coloring is a classic topic in graph theory and theoretical computer science. And the most well-known theorem is the four-color theorem, which states every map can be colored with 4 colors. And I think it is one of the most greatest achievements in 20th century mathematics and computer science. And its proof highly relies on computer programming. And second, graph coloring interacts with many other topics in graph theory, such as Ramsey theory, structural graph theory, and central. And third, numerous real-world problems can be modeled by graph coloring. Among them are scheduling, frequency assignments, and even statistic physics, just to name a few. So next, I will give you 2 examples to give you an idea how the graph coloring arises in real world. So the first example is called examination scheduling problem. So imagine students at a university have annual examination in all the courses they take. Naturally, examination in different courses cannot be held concurrently if the courses have students in common. The problem is, how can all the examinations be organized in as few parallel sessions as possible? Because if you consider to save some resources. To find such a schedule, consider graph G, whose vertex set is the set of all courses. So every course you introduce a vertex, and the 2 courses being joined by an edge if they have students in common. And you can think of it as a conflict. So the required minimum number of parallel sessions is the chromatic number of G. And the second example is called aircraft scheduling, which is of similar kind. So suppose you have K aircrafts, and you want to assign them to N flights, where the ith flight is during time interval AI and BI. So the question is, are K aircrafts enough? So we construct a conflict graph G similarly to the previous example. So for every flight you have a vertex, and the two vertices are connected if the corresponding time intervals overlap. Now the problem is equivalent to ask whether or not the chi G is at most K. And here, the graph we constructed is called an interval graph. And this graph is well studied and has very nice properties, so we can call it linear time. That means we can solve the problem pretty quickly and efficiently. And therefore, it is important to study the complexity of coloring problem. Because in reality, if you model your questions, you model problems as graph coloring, you would like to know whether your graph has some special properties so that coloring problem can be solved quickly. And this is what I am focused on. So here I'm focusing on classifying the complexity of K-coloring. So namely deciding whether the K-coloring is polynomial solvable or NP-complete. So I define the K-coloring problem as the following decision problem. So the input of the problem is just a graph G. And the question is there a K-coloring of G? And as you might learn from the course 705, the complexity of K-coloring for general graphs is as following. The two-coloring problem is polynomial time solvable, say using BFS. And in sharp contrast, the K-coloring problem is NP-complete when K is at least 3. So if a problem is NP-complete, it is unlikely to have a polynomial time algorithm. So how can we attack NP-complete problems? One common way is to consider subproblems. And in this case, for K-coloring, we can consider K-coloring on some restricted graph classes. And recently, people start to study K-coloring on graphs characterized by forbidding one induced subgraph. So what do I mean? So let H be a graph. We say a graph G is H-free if G does not contain H as an induced graph. So essentially, we just forbidden some pattern in the graph. For example, if the H is an H, if a graph G is, if you don't allow any H in the graph, then the graph is just some isolated vertices. So you can just use one color to color the graph. So as I said, recently, much attention has been given to classify the complexity of K-coloring H-free graphs. So for example, Kaminsky and Losing, they show that H-coloring is NP-complete for H-free graphs whenever H contains a cycle. So this is a very nice result. It says if H contains cycle somehow complicated, then you forbidden H does not make a problem easier. And based on two classical results, back to 1980s, we can easily deduce that K-coloring problem is NP-complete for H-free graphs whenever H is a forest, that means have no cycle, and H contains the vertex of degree 3. So due to the above two results, only the case where H is a linear forest remains. So what is a linear forest? A linear forest is disjoint union of paths. Of course, the simplest linear forest is just a path, and this is, in the remainder of the talk, we focus on the case where H is a path. So let P sub T denote the path on T vertices. So this graph is the graph of P5 path on 5 vertices, so just one next to each other. So before talking about the recent results in this area, I want to point out the monotone property of PT-free graphs. So, which means, suppose you know K-coloring is NP-complete for PT-free graphs, right? Then K-coloring is also complete for PT+1 free graphs. because the class of PT-free graph is a subclass of PT plus 1 free graphs. A graph does not have pass on T vertices, of course, does not have pass on T plus 1 vertices. And K plus 1 coloring is also NP-complete for PT-free graphs. You can have an easy reduction. Suppose you have a G which is PT-free, then you just add one vertex and adjacent connect it to every vertex in G. And let's call the new graph G prime. Then it's easy to see G prime has a K plus 1 coloring if and only if G has a K coloring. And further, because G is PT-free, so it's G prime. So based on that, if you want to prove NP completeness for K coloring PT-free graphs, we want K and T are as small as possible. The smaller K and T are, the stronger your NP completeness results are. And similarly, if you try to prove polynomial results, then the larger K and T are, the stronger your results are. And back in 2001, Ginger and Scale published the first paper on K coloring PT-free graphs. And then they proved 5 coloring is NP complete for P8 free graphs, and 4 coloring is NP complete for P12 free graphs, which are not bad. You can already see this K and T is not too bad. But later on, Lure, its central altogether, proved 4 coloring is NP complete for P9 free graphs. So this is an improvement of this result. And he reduced 12 to 9. So this is stronger. And 2010, Brosmar, its central altogether, proved 4 coloring is NP complete for P8 free graphs. And this is even an improvement of this result as well as this result. And for P6 free graphs, for P7 free graphs, the best we know is 6 coloring is NP complete. And on the positive side, we have following, and Hong, its central, proved the K coloring is polynomial for P5 free graphs for any fixed K. This is a really nice result because it solves K coloring for any K. And for P6 free graphs, the best we know is 3 coloring is polynomial. So along this line of research, people also consider some variants of K coloring. One of them is called pre-color extension of K coloring, so denoted by K, P-R-E-X-T. So the problem is you given graph G and some subset W that has been pre-colored with colors from 1 to up to K. And the question is there a K coloring of G that extends that pre-coloring of W? And in the list version of K coloring, you are also given a graph G, but with a set of admissible colors, LB, for each vertex. So the question is there a K coloring that respects this? Namely, can you color the graph such that the color for every vertex from its list? So you can see the K coloring is a special case of K pre-color extension, because if the W is empty set, the K coloring is just a K pre-extension. Pre-extension coloring, pre-color extension is a special case of list K coloring. So these are known results on pre-color extension of K coloring and list K coloring. For example, Brosmont, it shows that pre-extension coloring of 4 coloring is complete for P7 and so on. So to sum up, I have the following table. So this is the column is the value K, so we consider 3 coloring, 4 coloring, and the row is T, we consider forbidden paths on 4 vertices, 5 vertices central. And P here means polynomial, and NPC means NP complete. So for T equals 5, you know, for all the K it's polynomial, and for 6, the best we know is 3 coloring is polynomial, and for 4, 5, 6 we don't know, and so on. So what I have proved recently is the following. So I have proved these two new results. One is 5 coloring is NP-complete for P6 free graphs, and 4 coloring is NP-complete for P7 free graphs. So the significance of our result is this is the first proof showing that there exists some K coloring is NP-complete for P6 free graphs. And these two results improve all previous results in the literature, including those on pre-color extension and list coloring. And further, we have polynomial time algorithm for a subclass of P6 free graphs. So this is a updated complexity status. Before we have these two question marks, but now I have proved this NP-complete, this NP-complete, and by monotone property, this is also NP-complete, this is also NP-complete. So I think I don't have time to talk about proofs, so I just go into some open problems. And due to our NP-complete results, so the next question is 4 coloring P6 free graph, and we conjecture it should be polynomial. So as you can see, because this is NPC, so if we ignore the 3 coloring, the first row, the only question left is here. There's 4 coloring P6 free graphs. But in contrast, 3 coloring turns out to be very hard on PT free graphs. And very recently, Chernowski, its center altogether, made a big step by proving that 3 coloring is polynomial time solvable for P7 free graphs. However, it is hard to decide complexity of 3 coloring for PT free graphs for T is at least 8. So in fact, we don't even know if there exists some T such that 3 coloring is NP-complete for PT free graphs. So I leave this problem as the end of my talk. Thank you.
Let's thank our speaker. And as usual, how it happens, we welcome one question from the audience, and we have a prize to the person who asks the question. So anyone who's working maybe in this field and has interesting question to ask? Yes, Amir?
So you mentioned as application of the graph coloring, you mentioned two applications. So I'm just wondering how frequent is that in those applications you have H-free graphs, hat-free graphs, for example. So this is very free. So I know that you're doing some theory work, but I'm just asking.
Yeah, actually, I'm not quite sure if there is some direct application on H-free graphs. But yeah, as you said, I'm doing more like theoretical work. So the question is, the idea is if you forbid some pattern, so you just decide whether this makes problem easier or not. And maybe one of the example I can think of is like some social network, because we are so connected today. So in a social network, it's very unlikely say you know one person, the person know the other, and the person know the other, because after several steps you have some guy in the previous one knows the other. So it's unlikely to have a long induced path. I mean, so this is what I can think.
Okay, so let's welcome, thanks our speaker again for answering the question. And we welcome our second speaker, Margin.